Okay, welcome back to another video for the series, and today I decided to solve 2011 USAMO problem number 1, and that's because recently I've been studying more about inequalities, and I think this problem will help me a lot. So to be honest, I was not able to completely solve this problem, but I will still share what I tried. So yeah, let's get into it. So after looking at this inequality, I realized that we have the terms a squared, b squared, c squared, and also a, b, b, c, and c, a. And that's why I immediately thought of one of the inequality that we can derive from Shor's inequality, which is a squared plus b squared plus c squared, which is greater than or equal to ab plus bc plus ca. And unlike Shor's inequality, this works for all real numbers, so that's why I also thought of this. And now what I did is I multiplied 2 on both sides, so we get plus 2b squared plus 2c squared is greater than or equal to 2 times ab plus bc plus ca. And we know that if we add this thing one more time on both sides, like 2a squared plus 2b squared plus 2c squared plus 2b plus bc plus ca, this is obviously greater than or equal to 4 times plus bc plus ca. So this is what we know, and we also know that this is equivalent to the form that we see right here. In other words, for ab plus bc plus ca is less than or equal to a squared plus b squared plus c squared plus the rest squared, and then it is supposed to be less than or equal to 4. In other words, ab plus bc plus ca is less than or equal to 1. And the problem that I face here is that our inequality is actually flipped around here. So I should have find a way to set all my variables here and then somehow make the 1 into 3. However, I was not able to do that, and my solution stopped right here. So please comment something below, or feel free to email me if you think you have found a solution that could be continued from here. But for me, I was not able to continue, so I checked the solution, the official solution, and this is how it goes. So first, what they did is they expanded the inequality that we see right here. So we have a squared plus b squared plus c squared, and the same thing one more time, plus 2 times ab plus bc plus ca is less than or equal to 4. And that means a squared plus b squared plus c squared plus this is less than or equal to 2. Now, one thing that we should notice from here is that the left hand side of this inequality right here is cyclic. That means we can write it like this is, so we should prove that this thing is true. And before proving that, we know that we have 2 right here, so we can somehow try and use it, and we can do that by multiplying 2 on the numerator. So we know that this one is obviously less than or equal to 2 times all of it. So ab plus 2ab and squared. And also, because we know that this thing is less than 2, so we know that we can also write a new one where we have this expression is greater than or equal to the cycles of, and we have 2ab and then this whole thing right here. So we have c squared and ab plus bc plus ca. And what we can do from here is try and factorize them, like somehow factorize it. So you know that we can rewrite this as a plus b squared and plus c times, we have these three terms left, so plus a and c plus b, which is obviously cycles of 1 plus a plus b squared and c plus b. Now, what we can notice from here is that we might be able to use AMGM inequality here. So if I write this out, like here, I'll just write it as there's c. This is what we get when we expand it out. Now we know that this is equal to 3 plus these big things. I will just do this, I don't want to write them. And notice that when we multiply all of them, we might get 1 because the a plus b cancels out with the denominator here, and we also have b plus a here. And because it's a cycle, we can assume that other ones will work like that too. That means we want to multiply these three terms, and the way to do it is we can use AMGM inequality here. So we know that this is greater than or equal to 3 plus, using AMGM for this 3, we get 3 times cube roots of 1, which is simply 3. So we know that this whole thing is greater than or equal to 6. So this is greater than or equal to 6, and our cycle right here, this one, is supposed to be greater than or equal to 6. And notice that when we look at our inequality that we need to prove here, we just need to divide all of them by 2. When we divide all of them by, if we divide all of them by 2, we get the cycles of, and it's supposed to be greater than or equal to 3 because we divided 2 on both sides. And this inequality right here is the same as the one that we see right here. Therefore, we finished our proof. Now, I think this problem was especially interesting to me because normally I would not expand it. I mean, going from here to here was quite refreshing to me because, as I mentioned, I immediately thought of Schur's inequality here. And also, what was really interesting is that we had to take a closer look at this too. So this too was actually a really important factor to try and multiply 2 on both sides. And also, noticing the 2 right here and then substituting like this was also quite new to me. And also, I think another kick from this problem is, we need to notice that if we multiply these 3 terms, we get 1. And we should use AMGM inequality if we see that. So I think noticing that trying to use the 2 right here, and noticing that if we multiply these 3 terms, we get 1, and therefore use AMGM inequality. I think these are the 2 kicks for the 2011 USAMO problem number 1. Thank you for watching this video, and if you like the solution, please don't forget to share to anyone who loves math and is preparing for math Olympiads. And if you think there are better solutions, or if you have any comments or questions, please feel free to leave them in the comment below. Thank you, and see you in the next video for tomorrow's problem.